Welcome to the third lecture of Advanced Computer Architecture course. In the first two lectures, we tried to recap the basic concepts in computer organization and few performance evaluation methods. This lecture onwards, we are moving into the advanced architecture concepts, and to begin with, we will have instruction pipeline as the point of discussion for this lecture. Moving straight into the topic. In order to understand the concepts of instruction pipeline, let us first take a case study of a RISC microprocessor. MIPS is the RISC microprocessor that we are going to have for our case study in understanding the instruction pipeline principles. Processors are broadly classified into RISC architecture and CISC architecture based upon the implementation of various instruction set. Let us try to understand what is the basic difference between a RISC machine and a CISC machine. If all the instructions are of uniform length and they are also represented in a uniform length instruction encoding, and more or less if they take equal number of cycles to complete, then they basically belong to the property of RISC architecture. It is known as reduced instruction set computer, where a task is represented as a sequence of simple instructions in the case of a RISC. And when you move on to the CISC architecture, maybe with few number of complex instructions we can represent the same task. For example, consider the case of a task wherein you have to find out square root of a number. If we have a single instruction wherein you give the number as the operand and that will take care of finding out the square root, then it is actually a very complex operation that is being represented by a simple instruction. Whereas the same square root can also be done with the help of multiple simple operations, and that basically can be considered as a classical example of how a RISC processor works. A processor cannot support a complex instruction like a square root, but the task of finding out square root can itself be done with the help of simple smaller operations. Similarly, finding out the largest among a block of numbers, it can be represented as a single instruction or it can be a sequence of simple operations. In the case of a CISC architecture, you have instructions of variable length and they will take a variable number of cycles to complete. So, in today's lecture, what we are going to consider is a very popular RISC architecture known as the MIPS microprocessor. Let us try to understand what are the important architectural features of this MIPS microprocessor. MIPS is the abbreviation for microprocessor without interlocked pipeline stages. This processor has 32 registers and each register can accommodate 32 bits each. And the peculiarity is all instructions are of uniform length and it follows a load store architecture. When we had the discussion on what are the various instruction set architectures based upon where operand is located when it comes to an ALU instruction, we have seen about stack architecture, accumulator architecture, register memory architecture and register architecture, which is also known as load store architecture. So, the peculiarity of load store architecture is it is only a load and store instruction that is going to access the memory. When it comes to an ALU operation, both the operands are available inside the registers. So, we are going to have our further discussion on understanding of instruction pipeline with the help of the MIPS RISC architecture, wherein it has 32 registers, each of capacity 32 bit. The registers are named as R0, R1, R2, etc. up to R31. All of them are taking 4 bytes. All instructions are represented as 4 byte and they are of uniform length instruction and they follow the RISC load store architecture. Now, let us try to understand how instructions are represented in the MIPS microprocessor. Like what we have already mentioned, every instruction in MIPS is represented in 32 bits, and MIPS has basically 3 types of instruction: the R type instruction, I type and the J type instruction. R type instruction is also known as register type instruction, where the first 6 bits of the 32 bit instruction will represent the opcode, and then we have the source operand RS and RT, and RD is the destination operand, and then you have the function called and the shift amount. This section, this 5 bit is used only in the case of a shift operation. It will tell you how many bits you have to shift the operand. So, when it is an add operation, for example, this will tell you it is an add, and what category of add, the addressing mode will be specified in that function code, and these 5 bits each will tell you what is the register that you are going to talk about. Since there are already 32 registers, the first 5 bit will tell you what is going to be the register name for the first operand, next 32 will tell the register name for second operand, and the last 5 bit will tell you the register name for the destination. Now, when it comes to I type, we will be making use of 16 bits. The last 16 bit is used to represent a portion of an address or an immediate value, and the first 6 bit is opcode, and you will be having one source register and the other one is used as the base register. When it comes to jump instruction, you have a 6 bit opcode followed by the remaining 26 bit is called target. So, any jump that is possible in plus or minus 2 power 26 is been permitted here. So, broadly we have 3 types of instruction: R type, which has 3 register operands; I type, which has 2 register operand and a 16 bit immediate value or an address, and a J type, which has a 26 bit relative jumping address and an opcode. We will now try to understand the concept of pipelining in general. Prior to understanding about how an instruction pipeline happens, I would like to draw your attention to a laundry example. So, consider the case that we wanted to wash the clothes for a person A. Let us say the whole laundry operation is consisting of a washing unit, what is been so represented with this color, the yellow color, and the washing will take 30 minutes of time. After the washing, we are going to take the clothes from the washer and going to put it in the dryer, where the dryer will take 40 minutes to complete the task, and then we have 20 minutes to fold the clothes. So, altogether it will take 90 minutes for the clothes of person A to be washed. Once person A has completed the washing, then the person B is going to start, which will be taking 30 minutes, 40 minutes and 20 minutes each, and once B is done, then the work of C is been taken, and then you are going to complete the work of D. Each of them are going to take 90 minutes each. So, altogether when you are going to do the work like this, it is called a sequential laundry, where the washing process of the second workload will start only if the complete work associated with the previous workload is over. That means, washing of B will start, this entire process will start only if A is completely over. Similarly, C will start only if B is completely over, and D will start only if C is completely over. So, each of the sequential laundry is going to take 90 minutes each, and then we have total of 4 such workloads. So, 90 into 4, 360, that is essentially 6 hours will be taken to complete 4 loads. Now, in this example, we have to understand that the entire laundry process associated with a single task, say A, has to go through 3 subunits. A unit called washing, which will take 30 minutes to complete the washing process. The second unit will take 40 minutes for drying, and the last unit will take 20 minutes for folding. The peculiarity is all these 3 tasks are being done by independent separate units, and after the task is over, you have to take the clothes from one unit and put it in the other. Now, when the second stage, that is a drying process is in progress, the washing unit is free, as well as the folding unit is free. If you wanted to pipeline the whole operations, then the idea is we wanted to make sure that every unit is busy. So, when the drying of workload A is in progress, the washing unit can eventually start the washing for workload B. And once the drying is over for A, once the folding process starts, then the washed clothes of load B can be shifted to the drying operation. That is exactly what we are going to do with a pipelined laundry. So, in the case of a pipelined laundry, the concept is start work as soon as possible. If the functional unit that is going to carry out the work is available, start the work. So, when the drying is in progress, the washing for B will start. When the folding is in progress for A, the drying for B and washing for C is parallelly happening. So, if you look at this particular time window, then all the three units are busy. The folder is busy with completion of folding of the clothes of A, the dryer is taking care of the drying of B, and the washing unit is taking care of washing of load C. This makes sure that every unit is itself busy, and by which we can improve the throughput of a system. So, the entire pipelined laundry is going to take only 3.5 hours to complete the same task. So, what are the savings that we get? What are the characteristics of pipeline? Pipelining does not reduce the latency of a single task. As far as A or B or C is concerned, in the previous laundry example, the latency associated with a single task is not reduced, but the throughput, number of tasks that we can complete, is significantly improved. And the pipeline rate is limited by the slowest in the pipeline stage. In the previous example, we have seen the first unit is going to take 30 units, the second one is going to take 40 units, and the last one is going to take 20 units. So, considering this, I can start new work only at intervals of 40, because it is the second unit that is the slowest. The pipeline rate is limited to the slowest pipeline stage. So, in this case, at regular intervals of 40 minutes, new work can be initiated. And the speed up that we are going to get from a pipeline is equal to the number of stages. Here we have 3 stages, so roughly the speed up is 3 times. Now, when you have an unbalanced length of pipeline, for example, here you have 20, here you have 30, the other one is 40, it is not uniform length. This is slightly creating some performance issues. What if you are going to consider something like 10, 100 and 20, let us say these are the 3 stages of the pipeline. One stage is having very high delay, whereas others are having very slow delay. Here also we can initiate new task only once in 100 unit of time. So, this is an unbalanced, this is an example of an unbalanced pipeline. These kind of cases should be avoided, or if pipeline will achieve its full performance only if all the stages are having almost an equal pipeline latency. And then the last aspect of pipeline is, from one unit of pipeline, from one subcomponent of the pipeline, I have to take up the task and then feed it to the next one. So, that is an extra overhead, time to fill the pipeline and time to drain the pipeline. Once the task is done inside a pipeline unit, it has to be drained out from that unit and it has to be fed into the new one. So, this filling and draining is going to consume little bit extra overhead. Having understood the concept of pipeline with an example of a laundry, now we will try to correlate the concepts that we have discussed just now in the case of pipeline circuits. We have already mentioned that with respect to execution of an instruction, there are various sub stages like instruction fetching, decoding, executing the task, storing result and all. All these are done with the help of logic gates. So, if you consider the entire operation associated with execution of an instruction like fetching, followed by that we have the decoding operation, and then we have the operand fetch or execution, all these stages, if you consider all these as one unit, we have a single monolithic unit which will take. So, this particular combinational system or this circuitry will be having an address as its input, and then the output is the instruction that is present in the address is fetched, decoded, executed, and the result is being stored. That is what we have if it is a single monolithic design. Now, that is not a modular structure. From that, can I subdivide the entire monolithic big design into smaller subcomponents where each of this component is taking care of one aspect of the execution of the instruction. We are going to divide the entire circuit into multiple smaller components. So, when you apply pipelining, pipelining partitioned the system into multiple independent stages with added buffers between the stage. As we have already discussed, pipelining can increase the throughput of a system. Consider this diagram wherein just imagine that this is the big circuit that will take care of execution of an instruction. So, you are going to give the address. This address is being fed into this logic, and this logic is going into memory, bringing the instruction, decoding it, and doing all operations needed with it. At the end, we are going to have a completion of the execution that is being done. Now, the second line tells that rather than considering the entire logic as a big logic with n gates, can I divide them into roughly 2 halves, each with n by 2 gates, and providing a buffer in between them. So, the same task now I am going to do it as 2 subtasks. So, the left side subtask consists of roughly n by 2 gates. It will do some kind of an operation, and whatever partial operation that is being done, the result is kept in the latch, and after that when it is been triggered, the second half is going to take the partially process the result from this L and do the operation. When the second unit is taking care of the operation, when this unit is busy doing the operation, the first unit is ideally free. It can take up a new task. Similarly, I can divide further also, and this whole approach of dividing the actual circuit, which was n logic gates, into smaller subcomponents and trying to interface with them with latches is called pipelining inside the circuits. Essentially, this is the same thing what we are going to look into. Can I divide my entire execution into smaller components like instruction fetch, instruction decode, execute, like that. Now, I would like to draw your attention to the MIPS microprocessor which we have just introduced and incorporating the pipeline principle that we discussed. So, in an unpipelined RISC MIPS microprocessor, there were 5 different components which will take care of the execution of a single instruction. These are instruction fetch, followed by instruction decode and register read. The third stage is execution or address calculation. Fourth one is memory access, and the fifth one is write back into the registers. This is roughly what you can see from this diagram. There exist some units which will take care of the instruction fetching operation, and then we have the instruction decode and the register fetch operation. Then it is execute or address calculation, followed by memory access, and then at the end it is the writing back. Now, when you are going to pipeline this, then with whatever you have seen, the various 5 stages, between 2 stages, let us say stage 1 and stage 2, we are going to add an interfacing in between them, and that is called the pipeline registers that is kept between various stages. We are going to give names for each of the stage. They are called IF, second stage is ID, third stage is EX, fourth stage is MEM, and the fifth stage is write back. So, depending on the stages, these pipeline registers are also given a name as per this. This is a pipeline register that is in between IF and ID. So, we call it as IF/ID register. This is a register that is between ID and EX. So, the name is ID/EX. Similarly, EX/M, MEM/WB are the name of the pipeline registers. We will now try to see each of these sub stages in detail and try to understand what are the operations that are being done. So, the first one is known as instruction fetch. This is the circuitry associated with the instruction fetch. What it does is, based on the program counter value, fetch the instruction from memory. So, this is the address that is been supplied by the program counter. It goes to the instruction memory or memory in which the instruction is being stored, and the contents of that is being taken and that is being stored in the pipeline register IF/ID. In the meantime, we are going to update the PC such that we will come to know from where the next instruction is to be brought. Since it is a RISC architecture and all instructions are taking uniform length, the next program counter value can be easily obtained by finding the PC equal to PC plus 4. So, whatever is the new PC that is being added to 4. So, it is very easy as long as all instructions are of uniform length. Updation of PC is a relatively simple step. If the instructions were not of uniform length, like what we see in CISC, some of the instructions are 1 byte, some are 2 bytes, some are 8 bytes like that, then after bringing the instruction, we have to understand how long the instruction is, and only then we can increment the value of PC. So, the basic operation that is being done in instruction fetch one is, based on the program counter value, go to memory, bring the instruction and update the program counter value by adding 4 to it. This much is done in the instruction fetch state. Now, moving on to the second stage. The second stage is also known as instruction decode as well as register fetch cycle, which is abbreviated as ID. So, whatever you have done in the instruction fetch stage, an instruction is available in the IF/ID register, and from there you do some operation. At the end of this unit, the ID/EX register will contain the resultant of the decoding and register fetch operation. The first task associated with ID stage is decode the instruction, and if at all there are any register values that are to be read prior to execution operation, then read the register content as well. It is also known as fixed field decoding. For example, consider the case that you wanted to perform an operation add R1, R2, R3. Let us say the binary representation of it in hexadecimal is A3, 01, 02 and 03. As an example, consider the case that this is the 32-bit value which correspond to an add R1, R2, R3 operation. Let us imagine that this represents opcode and this represents R1, another one represents R2 and this represents R3. R3, this is R2 and this is R1. So, when we get this 32-bit instruction, the decode unit can cut this 32 into 4 components, each of 8-bit each, and the first 8-bit is analyzed to understand what the opcode is. We have already seen that opcode means what is the operation, and the remaining 3 8-bit units will tell what are the source operands, and this can be done parallelly. So, I should not even wait for what the opcode is. I can go and find it out, the 8-bit values that will tell you what is the name of the registers. This process is known as fixed field decoding, as the number of bits required to represent the opcode and represent the operands are being predefined. It can be also a case that if the instruction is going to be a load word instruction, we see that this is a RISC microprocessor, and RISC use load and store instructions in order to transfer contents from memory. So, load word R1, 8 of R2, let us say it is an instruction whose meaning is I have to transfer the contents from a memory location into a register. Let R1 be the destination register. So, the contents of memory location whose address is R2 plus 8. R2 is another register, go to R2, find its 32-bit value, that is the content of R2, add 8 to it, that is the absolute address. Go to that memory location, transfer that contents into R1. This is called load word. Now, if it is a load word instruction, then this portion will tell you that it is a load word. this will tell it is an R1, this is going to tell it is 8 and this is telling it is R2. So, in this case content of R2 is to be read and this should not be treated as R8. The immediate value of 8 has to go. So, if the instruction is of an add type, then this has to be R2. If the instruction is of load type, then rather than considering this as R8, it should be considered as an immediate value. To make things simple, without decoding, the second stage won't know whether it is an add operation or it is a load operation. If it is an add operation, then it has to be understood as R2. If it is a load operation, it has to be understood as a scalar value 8. So, both the possibilities are being considered, and once you understand what is the operand, in this case the value of R3 as well as the content of R2, contents of R2 and R3 both are read from the register file and they are brought into the IDEX register. So, let us try to understand what this operation is being done. In the stage, in an ID stage, decoding is done to understand what the opcode and operand is, and after identifying the operand names, it has been gone into the register file and the content of the source operands are being fetched from the register file and are kept in the IDEX register. Once we come to know that it is a load or a store operation, then a displacement value, a 16-bit displacement value is coming, as well as the name of a register is coming. So, then the content of the base register only is going to come. So, that is being supplied. So, depending on the opcode, the activity that is being carried out in the ID stage is going to vary. Either it will find out the values of two of the source operand, let us say R2 and R3, and bring its contents to IDEX register, or it will transfer a 16-bit immediate value and the content of a register when it happens in the case of a load word. In any case, the values will reach the IDEX register. Now, the third stage is known as execution stage. It is also known as effective address stage. The abbreviation given to this stage is EX. The operation that is carried out in the EX will vary depending upon what is the operation. Consider the case that the operation is a memory reference, that it can be a load word operation or a store word operation. We know that in the case of a load word or a store word, there is a register name that is associated, and so consider the case that we are going to take an example where the load word and store word is being shown like this, where the load word is load word R1 comma 8 of R2, or if it is a store word R1 comma 8 of R2. What does it mean? In the case of a load word R1 comma 8 of R2, the address is given by R2 plus 8, that is been transferred to R1. It is a copy from memory to processor, that is a load operation. Whereas in the case of a store, the content from R1 is moved to memory, whose address is given by 8 of R2. In both these cases, that is, if it is a memory reference operation, then in the execution stage, in the third stage of the instruction pipeline, content of R2 is added with the immediate value 8. That is, calculation of the effective address is what happens in this cycle. Whereas, if the operation is a register ALU operation, like what we have seen, like add R1, R2, R3, then it is actually adding of R2 is going to happen here. The content of R2 is added with the content of R2. So, if it is an arithmetic logic operation wherein both the operands are registers, then the actual execution is carried out in the EX stage. Whereas, if it is a memory reference, then effective address is computed. So, if you look at the name, either the execution takes place or the effective address calculation takes place in the third stage. The next is the fourth stage. It is also known as memory access cycle, called MEM stage. This stage is used only by load and store instruction. If it is an ALU instruction, then no operation is carried out in the mem stage. Whatever was the result that was available in the EX mem register, that is simply bypassing into the mem write back register if it is an ALU operation. If it is a load operation, whatever is the address that is calculated in the previous stage, from the address the contents are loaded. If it is a store operation, then whatever is the address and whatever is the data that is available in the EX mem register, that is being written into memory. So, if it is a store, it gets over here. If it is a load, then the value is taken from memory. Just to summarize, the mem stage is the fourth stage. By the time you reach the mem stage, if it is an ALU operation, already the execution is over. If it is a memory operation, the address is computed. For memory operations, using the address, the memory access takes place. If it is a load operation, then with respect to the effective address that is calculated in the previous cycle, go to memory, access the location and take the value, and the value is now stored in this mem write back register. For a store instruction, already the operand value is available in the EX mem register, as well as the address is also available. So, with the address, with the data, go to memory and complete the store operation. So, store operation is going to get over in memory and nothing comes out to the mem write back register. And the last stage is known as write back. Any write operation that is to be performed into a register, then it is the fifth stage that will take care of it. So, for register ALU operations or load operations, the destination is a register. For example, load word R1, 8 of R2 or add R1, R2, R3. In both these cases, in the case of an add, R1 is a destination. In the case of this load word, R1 is a destination. Writing into R1. So, what is to be written into R1, that will be available in the mem write back register. In the case of a load, the loaded value is available here. In the case of an add, the resultant of the add is transferred from EX mem to mem write back. This writing happens at the fifth stage. So, any reading from a register that is happening in the ID stage and any writing on the register that is happening in the write back stage. So, here logically it is being shown with this red color arrow that moves from the write back into the register file that is being accessed in instruction decode. It does not mean that the register file is present inside instruction decode. The instruction decode stage will access the register file and read the values, whereas the write back stage will access the register file for writing the result into it. So, that constitutes the 5 stage of instruction pipeline. You fetch the instruction, decode and read the registers, execute or calculate the effective address, for load store perform memory access and write the result back into registers. So, we can see that all these pipeline stages are having the pipeline registers and they are connected to the same clock. Once the clock is ticking, whatever is available in your input pipeline register that acts as the input to the combinational block, perform the operation, write the result into the output pipeline register. So, the output pipeline register, this is the output pipeline register for the second stage and this is the input pipeline register for the second stage. The output pipeline register for the second stage is acting as the input pipeline register for the third stage and so on. So, every unit at the beginning of the clock cycle will accept the input from the input pipeline register, perform the operation using its combinational block and write the result in its output pipeline register, which in turn is to be used by the next subsequent stage. So, we will try to summarize the 5 steps of RISC data path. You have an instruction fetch wherein PC based on PC value the location is being fetched from memory and updation of PC happen. In instruction decode, decode the instruction and read the register contents. It is a fixed field decoding. If you wanted to have equality check of 2 registers, let us say R1 equal to R2, that also is done in this stage, and computation of branch target address also happen in the ID stage. The EX stage takes care of effective address calculation for data access instruction, and for any other ALU operation the actual instruction is being carried out here. For mem access, accessing the memory using the effective address that is computed using the EX stage, and the write back stage writes the resultant of an operation that has to be reflected inside a register. So, in short, branches will typically get over in 4 cycles, stores also will get over in 4 cycles, all other instruction will go to the 5th cycle wherein a write back is happening. So, if you try to visualize a pipeline, consider the case wherein on x axis the clock cycle numbers are being represented and on the y axis we have the instruction counts. Each of the instruction has to pass through 5 stages. So, consider instruction number I, where on the first clock cycle the instruction fetching is happening and then second clock cycle perform decoding, then followed by EX, MEM and write back. At the end of the 5th clock cycle, the ith instruction is reaching its write back stage or it is completing the instruction's execution. When we applied pipeline principle, in I plus 1th instruction goes to instruction fetching in the second clock cycle. When the first instruction is in the decode stage, the second instruction is in the fetch stage. Like that, the second instruction will get over in the 6th clock cycle. So, after the initial delay, the first instruction is getting over at the 5th clock cycle. Thereafter, in every clock cycle, one new instruction is reaching the write back stage or the instruction is getting completed. If you look at the 5th clock cycle, you can see that the WB stage, the write back stage is dealing with the write back operations of the first instruction. The MEM stage of the instruction pipeline is taking care of data memory access of I plus 1th instruction. The EX stage is taking care of the execution stage of I plus 2 instruction. The ID stage is taking care of the decode and register reading of the I plus 3rd instruction, and the IF stage is taking care of the fetching of the I plus 4 instruction. So, all the 5 units of instruction pipeline are busy handling their respective operation and they are busy with 5 different instructions. So, we can see that multiple instructions are already there in the pipeline and this will improve the performance because the throughput has substantially increased. For every clock cycle, one instruction is getting over. This is yet another visualization of the pipeline. Previously, we were telling what are the operations to be done. Here, this diagram shows which are the functional units that are busy. First one is the instruction memory. So, you fetch instruction from the instruction memory and then you decode and read from the registers. You use ALU for address calculation or for arithmetic operation. Then you have the data memory and then you write the result into registers. So, if you look at down, the register file is been busy at clock cycle number 5. The register file is been used by the first instruction for a write operation. The data memory is used by the second instruction for a memory access. The ALU is used by the third instruction for an ALU operation or for an address calculation, and the register file is again used for a read stage in order for the register read of the 4th instruction and so on. So, we have seen what are the 5 different stages associated with the instruction pipeline of a RISC microprocessor. So, this shows the ideal case wherein at every cycle we should be able to start a new instruction, and after the initial latency is over, for every cycle one instruction is to be completed, and we make sure that every instruction has to be represented as a sequence of 5 sub operations. It is a bit challenging design. So, having said all the rosy things or things, the promising things about an instruction pipeline, let us now try to understand what are the challenges in implementing this. Coming to pipeline issues, the ideal case we feel that uniform subcomputation, the computation to be performed can be evenly partitioned into uniform latency subcomputations. We have seen 5 subcomputations that are associated with the execution, and our assumption was all these 5 are going to take same amount of time. But in reality, we will have internal fragmentation. Not all pipeline stages may have uniform latency. So, how can you to resolve it? Wherever possible, memory access is a critical subcomputation. When you are going to access memory, since memory is a slower device and processor is much faster, any kind of access to memory is going to take more amount of time unless we keep very high speed cache memories. but it is not possible always to accommodate all your instruction and data in cache memory due to its limited size. So, wherever possible try to reduce memory computation, but we are in the case of a RISC architecture we use only load and store instruction that take care of memory. So, memory addressing modes wherever possible should be minimized, faster cache memories has to be employed. These are the implications of instruction set architecture. If you look into the second issue of pipelining is the ideal case says that identical computation. The same computation is to be repeatedly performed on a large number of inputs data sets. So, what we feel is we have 5 different stages and these 5 stages have to be done for every instruction that this processor is doing. In reality, we know that some pipeline stages are not used by every instruction. For example, the MEM stage is not used by an ALU instruction. Why we keep this? We keep things very simple. What is the impact of instruction set architecture? You reduce the complexity and diversity of instruction. Don't go for a wide variety of instruction. Keep all instructions of uniform type so that we can accommodate all these instructions in various 5 stages of an instruction pipeline. So, reduce the diversity of instruction, make all instruction look similar so that I can make use of all of them to pass through the common set of stages. The second point is the RISC architecture use uniform stage simple instruction. That is one reason that your RISC architecture will beautifully fit into this 5 stage instruction pipeline. And the third pipeline issue is independent computations. Our idealistic assumption is all instructions are mutually independent. What do you mean by mutually independent? I can run an instruction without waiting for its predecessors to get over. So, if an instruction is dependent on some other previous instruction, only if the previous instruction is complete, then only we can run this new instruction. So, the whole concept of pipeline what we have seen is that in every clock cycle one new instruction is being fetched without looking into the outcome of the previous instruction. So, what is the reality? If you assume this real time case, the reality is pipeline stalls will be created, we cannot proceed. Sometimes we may have scenarios in which a later computation may require the result of an earliest computation, that is called dependency between instructions. And what is impact of instruction set architecture? Wherever possible try to reduce memory addressing mode. You can have dependency, but if the dependency is between then registers. So, consider the case that you have an add instruction with R1 as the destination operand, R2 and R3 are the source operands. Now, let us consider another instruction, let us say subtract R4, R1 and R5. So, we can see that as per the convention that is being used, this R1 is the place where I write the result of R2 plus R3, and here the same R1 is used as the source operand. So, the subtraction instruction is dependent on the add instruction because the result of add instruction R1 is needed for subtraction to begin operation. So, but this is easy to understand because both of the operands, that is from the name R1, it is easy for us to understand that there is a dependency. So, subtraction instruction should not run. But sometimes we may get certain scenarios in which it is difficult for us to find out dependency. Here the dependency is easy to find out because of the similarity in the name of the registers. Now, we can have dependency when we use memory addressing modes. So, consider the case that I am going to store a word, the content of R6 is going to be stored into 16 of R1. So, go to R1 and then add 16 to it, that is a memory address, and to that address content of R6 is being written. Now, let us imagine there is another load word. So, consider these two instructions. If you look at them, there is no operand that is common. The first store word has one of the register is R6, the other register is R1. The second instruction has R8 and R2 are the registers. There is no similarity between them. So, if generally we ask, is there a dependency between this instruction? We do not find a dependency straightforward, but there can be a case that 16 plus content of R1 if it is equal to 8 plus content of R2, which we will come to know only at runtime. If R2 plus 8 is same as R1 plus 16, then actually store is going to write into a location from which the load is going to read. So, even though there is no dependency that we can detect from by looking at similarity of registers, still there exists dependency. So, wherever possible, try to reduce memory addressing mode because dependency detection is very difficult. Use register addressing mode wherever possible because it will help the compiler in easy detection of registers. So, these are the three pipelining issues that we have seen, and that concludes our lecture 3. So, before going to wind up, let us have a quick recap. Today, we were trying to understand what is the basic concept of a pipeline, and we have analyzed the example of a sequential laundry versus a pipelined laundry, and drawing conclusions from that, we try to understand how pipelining can be applied on circuits. We familiarized with the RISC MIPS microprocessor, wherein we have 32 registers there. All the instructions are represented using 4 bytes, uniform length instruction. It is a load store architecture. And the instruction pipeline consists of 5 independent subcomponents: IF, ID, EX, MEM and write back. And we have seen that what are the functionalities involved in each of these stages. And having said all the interesting things about pipeline, we were trying to understand what are the practical limitations in implementing the pipeline, starting from uniform subcomputations, then similar subcomputation that has to go through, and independent computations between instructions. So, try to read the textbook, get familiarized with the concept, and we are posting few assignment questions for you to get a deeper grip on the topics that is been covered in the first 3 lectures. Try to work on it. Thank you.